Hey, this is Israel Adika, a PhD student in computational applied statistics. I'm here to present my technical report and show us some codes on the array smoothing and standard deviation analysis using the C programming language. All right. So, um, my introduction goes this way. The construction analysis of a program, that is a C program intended to investigate how data smoothing affects statistical variability, and this is documented in this report. Now, in my code, in a detailed smoothing technique is applied. Arrays of random, double precision, floating point values are generated, and their statistical features are computed, and then the quantitative reduction of data variability as indicated by the standard deviation is demonstrated. Now, that's just a brief. So my main principal aim is to illustrate mathematically and in code the impact of smoothing transformations on data distributions with a focus on lowering standard deviation while preserving the data set's key features. Yeah. So now let's go straight to the, I don't know if you can see my screen. Yes. So we have, um, just a moment. So I'm using the party programming tool to run the C program. Yeah, so this is my editor. So I include all the libraries, and then we're just heading straight. Yeah. So going into the main work. So my code contains four main components of the implementation to offer a comprehensive analytical framework. So we have the random array that generates scaled random values with controlled distribution. And then we sum the cumulative, or we compute the cumulative sum of array elements. And then we calculate the population standard deviation to measure data spread. And then we smooth. We apply the weighted smoothing operation to reduce local variability. Right. Okay. So let's get to work. Um, so up here, my first is we fill an array with random double values between 0 and then the given scale. Right. And here we have the array. So the array is to fill with random values. The size is basically the number of elements in the array, and then we have the scale, the maximum value for the random numbers, right? And then our next set of codes, this highlighted one, it adds up all the numbers in the array, right? So just like I said, the four main components, we do the random, we sum, calculate the standard deviation, and then we do the smoothing, right? So this is where we sum up all the numbers in the array, and when we move further, let me use the cursor a bit. Yeah, so this section of the code, just a moment. Yeah, so this section of the code from this point downwards, that's where we find the standard deviation of the array using the population formula. So again, we have the array, the size, and then we return the standard deviation. And it will be 0 if the size is invalid. Okay, let's keep going. And then here, at this point, we do our smoothing. So here, from this point, think all of this, where we smooth the array by blending each middle value with its neighbor. Yeah, the formula is the new value is equal to the weight times the current value plus 1 minus the weight multiplied by the left plus the right, all divided by 2. Right, so that's the code for this part. And um, in this part of it, we save a copy of the original, we smooth the inner parts, and then we back up. And we come to the final. So the main part is where we generate the random numbers, smooth them, and then we show the difference. So the main part of the code here, we again generate the random numbers. So we seed the random number operator right from here, and then we check the original seed. We do the smoothing at this level, and then we show the smooth array. Show the smooth array, and then we check the new spread, and then this is a quick summary. All right, so this is already saved. All right, so let's go to running it. So here I have my compiler, the G++. I named the file G++ smooth hyphen underscore std, which is standard deviation.cpp. Yeah, and then I run it. Okay, so these are my results. And basically the results states that the smoothing operation demonstrated significant effectiveness in reducing the data variability, and we could see the standard deviation dropped from 2. Okay, so right here, because we are doing a number of iterations, right here the spread reduced from 3.2096 to 2.0179, and the change amount is 1.1917, a percentage change of 37.13%. Yeah, if we do another, we have this 2.70972 to 2.0705, a change amount of 0.6391, percentage change of 23.59%. And so depending on the number of iterations you make, yeah, the significant reduction of the variability in it after the smoothing is done. Yeah, so this result is just to indicate that the smoothing acts as a low pass filter, and also as a discrete conversion operation. So while keeping low frequency trends intact, it minimizes high frequency component, the rapid changes. So basically, by reducing statistical fluctuation in data sets through the smoothing process, this program effectively illustrates the basic idea. Strong framework for examining the effects of the weighted averaging on data distribution suffered by the implementation, with a focus on standard deviation reduction. So in our code here, my achievements included a modular, well-documented code base that compiles without warnings or errors, a clear demonstration of the smoothing effect with quantitative metrics, proper handling of edge cases and memory management, and then it's user-friendly, it's readable, and for future works, with I think that maybe we can implement multiple smoothing passes with different weights, We can incorporate statistical significance testing for observed reductions and maybe include some graphical visualizations. Yeah. Thank you. Thank you. And so that's the end of my presentation. Thank you.